In this section, we're going to again look at the hypothesis testing for two samples and their means, but this time the standard deviations are unknown. Last time we did know what sigma 1 and sigma 2 are. Now, there are two possibilities, and the equations are slightly different depending. If we do not assume that sigma 1 equals sigma 2, and the two samples are independent, both are simple random samples, both samples are large, then our t-score, and again we use t-score because we don't know the sigmas, looks as following. x1 bar, subtract x2 bars, subtract the difference in the population means, over, and then notice this one has the s's instead of the sigmas that the z-scores had. The degrees of freedom will be the smaller of the two. So that's the equation we use for our test statistic if we do not assume that sigma 1 equals sigma 2. On the other hand, if we assume that they are equal, and all the rest of the information is true, two samples are independent, random samples, large, etc., then we replace what we had down here with what's called the pooled variance, and it's a little bit more intimidating looking, but it's really just the n-1s for each one times their variances and so forth. And we have to use all of this instead of that. And so it is an important consideration in the problem. Is this one where we assume that sigma 1 equals sigma 2, or is it one in which we don't make that assumption? And in truth, sigma 1 and sigma 2 are rarely known, and so usually if you don't, you're going to assume they're unknown, but you're not necessarily going to assume that they're equal. Alright, so just like the last section, same steps. Okay, the only thing that's changed is what's the test statistic equation, and because we don't know sigma, we're going to do t-scores instead of z-scores, but in the traditional method, last time we compared two z-scores, this time we're going to compare two t-scores. And then likewise, we can do the confidence interval method, and really all that changed was we have a different margin of error equation, and really it's because we have sample variances instead of population variances, and we have t-scores instead of z-scores. So that's the main change. To repeat, what's the claim, counterclaim, what are the null hypothesis and the alternative hypothesis, alpha is usually given to us, what's the relevant statistic, determine the sampling. In this case we're going to be using the t-distribution, the student t-distribution. Find the test statistic, the critical values, the critical region, and so forth. Reject the null hypothesis if the test statistic is in the critical region. In other words, the t-score is even more extreme than the one that you calculated from alpha. And then restate the results in simple terms. So let's look at a couple of examples. So, table below lists the results from a study using 30 randomly selected sedans from the manufacturer and 32 from its leading competitor. At alpha equals 0.05, can you support the manufacturer's claim that the mean driving cost per mile of its sedans is less than that of its leading competitor? Assume the population variances are the same. So again, the whole purpose of this chapter is you can look and say, yeah, they're different. They have different means, they have slightly different standard deviations. The real question is that difference significant enough? Is it really that different? Or if you had done a second sample, could you just get that by random chance anyway? So we're really trying to find out is if the difference between two samples tells us more or not. So, are the minimum requirements met? Well, we don't know the sigmas. Samples are random and independent. N1 and N2 are both at least 30, so we're okay on that bound. So let's look through the steps of the traditional method. And again, the traditional method is, in this case, is we're going to have the comparison of two t-scores. One based on alpha, and the degrees of freedom, the other based on our test statistic. So, claim, the one is less than the other. Counterclaim, no, it's more than. Null hypothesis gets the equal sign. And, just to repeat, a lot of times in the book, if that's the alternative hypothesis less than, then they'll make this greater than or less than. But it's still got the equal sign in it. That's the key. Alright, alpha is 0.05. We use the t-distribution, which is table 5. The variances are equal. So our degrees of freedom is based on N1 plus N2 minus 2, which is 60. The left-tailed test because it's less than. So based on 60 is our degrees of freedom and our alpha of 0.05 in the left tail, we get a critical t-score of negative 1.671. By the way, if we were looking at table 60 and the 0.05, you might say, well, no, it says it's positive 1.671. Okay, if it's a greater than case, it would be positive 1.671. If it's a less than case, it's negative 1.671. Alright, since the variances are considered to be equal, we have to use the pooled variance calculation. And so there's the equation repeated. Now we're going to plug in all our numbers. 30 minus 1 to give you 29. 32 minus 1 to give you the 31. That's the S1 standard deviation for the manufacturer, the standard deviation for the competitor. Put all those things together, and that's our pooled factor. So basically our equation looks like this. Now it's similar to what I had before. It's just, remember, this got replaced with all of that, and so instead of writing it all again, I just put the SP. So SP equals all of that, and that's down there. So 0.48 minus the 0.51, subtract 0, why 0? Because again, our null hypothesis, the assumption is they're equal. So that's what we're testing. Are they really equal? We get a negative 1.93. Now, we make our comparison. Negative 1.93 is less than, more extreme than negative 1.67. It's in the rejection area. Therefore, we reject the null hypothesis. The null hypothesis is they're basically the same thing. We're rejecting that. So we are saying that the difference between these two is enough to support the claim that, in fact, the mean driving cost for the sedans of the manufacturer is less than the mean driving cost of his leading competitor. Now, if we wanted to do confidence interval method, again, the steps 1 through 5 are all pretty much the same thing. This time we have to do our margin of error. Notice it's the same equation we were doing before. Okay, the only difference is we have the critical t-score as part of it. So we get the 0.026. 0.48 subtract 0.51, that's going to give us 0.03. So it's a negative 0.03 because the 48's less. So negative 0.03 subtract a negative 0.026. Negative 0.03 plus a 0.026. When we work it all out, our interval goes from negative 0.056 to negative 0.004. Note that the entire interval is negative, below 0. Therefore, it does not contain 0. The null hypothesis is mu1 minus mu2 will be 0. That's what we're looking at, mu1 minus mu2. Since it does not fall within the confidence interval, we reject the null hypothesis. And we say there is sufficient evidence to support the manufacturer's claim. Now, before we move on, I might point out that that is pretty close to 0, 0.004. So we can say we have evidence to support, but we can also acknowledge that it's just barely there. It's almost up to the 0, and therefore maybe we wouldn't insist on this result as strongly as if, for instance, this whole range had been like from -3 to -2 or something. So keep that in mind. When the entire range is just barely off of our null hypothesis, it may be that while we do have the evidence, it's not very strong evidence. All right, now let's look at a second example. This is a table below. This results from a study of a number of words that samples of men and women spoke in a day. Use a 0.05 significance level to test the claim that men and women speak the same mean number of words in a day. This time we're not going to assume the unknown variances are the same. Last time we did, this time we're not going to. Okay, so there are, again, we don't know sigma. We don't know sigma 1 or sigma 2, but we do have our two samples. We had 186 men who spoke, on average, 15,668.5 words per day, with a standard deviation of 8,632.5. And we have a sample of 210 women who spoke, on average, 16,215 words per day. And then their standard deviation was 7301.2. So again, what is it we're really after? What we're really after is, yeah, they're different. But are they different enough to support the claim that men and women speak the same number of words in a day on average, or that they don't? Okay? So these are different. But are they that different? That's what we're going to really test. So, are the minimum requirements met? Yes, they are. We don't know the sigmas. Samples are random and independent, but N1 and N2 are at least 30. Okay, let's look at the traditional method again. This time the claim is they're the same. So the counterclaim is that they're not the same. However, the null hypothesis always gets the equal sign. So the alternative is actually the counterclaim. We're using alpha of 0.05. We're again using t-scores in table 5. In this case, our degrees of freedom is the smaller one. 186 is smaller than the 210. So 186 minus 1, 185. Now, depending on the table you have, there may not be a line for 185, and the table I used, the closest one was for 200. So it just depends on the table. You can, of course, use technology to get the exact value if you wanted to. With the table I used, also because it was two tails, alpha 0.05, the critical t-score was plus or minus 1.972, using 200 as the closest degrees of freedom. Alright, not quite as horrendous an equation to figure out the test statistic for the t-score. But we'll go ahead, plug in all our numbers, and here's my t-score, negative 0.6755. That's what the critical value was. That's what I needed to be outside of. Clearly, that's closer to 0. I'm not going to be outside of it. Okay, and therefore we fail to reject the null hypothesis. Okay, it is not in the test statistic. Now, it might be a little bit confusing to you to say 0.6 is bigger than 1.97, but they have negative signs. So this is closer to 0 than that one. So that's why it's bigger. Again, note the rejection area is outside of the critical t-score of 1.972. In other words, 0.6755 is closer to the center than negative 1.972. When you are going to reject something, it has to be further out. It has to be more extreme. And therefore, since we fail to reject the null hypothesis, there is not sufficient evidence to reject the claim that men and women speak the same mean number of words a day. Or another way of putting it is, yes, the numbers are different, but not different enough that the claim that they speak the same number of words each day couldn't still be true. Okay, confidence interval method. Let's take a look at that. And again, this just gives you an example so you can see how the one set of equations looks versus the other. Same steps 1 through 5. Find our margin of error. In this case, the margin of error comes out to be 1595.36. The difference in the means was 546. So I have negative 546, subtract 1595. Over here I have negative 546 plus 1595. And so I go from a negative value to a positive value. Since this goes from negative to positive, 0 has to be in there somewhere. It has to contain 0. And if we go back, my null hypothesis was they were equal. And if they're equal, then when we subtract them from each other, we're going to get 0. So, since the interval contains 0, we quite possibly could have mu1 equal mu2, and therefore we fail to reject the null hypothesis. There is not sufficient evidence to reject the claim that men and women speak the same mean number of words a day. And so, one example in which we had to use the pooled variance because we assumed that even though we didn't know what the standard deviations were, what the variances were, we said they were equal. And one example in which we don't assume that they are equal. And so it changes the equation slightly, but other than that, pretty much all the rest of the steps are the same.